John Duffield. Welcome, John.
Richard, hello.
Hello. Are you well?
Fine, thanks. You too?
Yes, I'm fine, thank you.
Good.
Did you enjoy the ride?
Lovely, lovely.
Okay, now we're here to talk about physics. And could you start by telling us, John, what drew you to writing about physics? Because I think there was a little bit of frustration and, which brought you to write this book and your internet articles. Am I right in thinking that?
Yeah. I'm an IT guy with a lifelong interest in physics. We've got two teenage children. I was disappointed that they gave up all of their science subjects. When I asked them about it, they told me the most exciting thing they'd done was timing a pendulum.
Right.
There were no Van de Graaff generators. There was no wow factor to it anymore.
Okay, and you were very sad when the maths tower at Manchester University disappeared.
Yeah. To me, it was symbolic. It was inspirational. It was a thing that put the campus on the picture postcards and on Skyline.
I've got a picture of it here.
It was demolished in 2005, and it was somehow symbolic. There was something wrong in demolishing such an icon.
Right.
I wasn't happy about it. It disturbed me. It bothered me.
Symbolic of the demise of maths and physics in general in our culture, I think.
Well, there is a new building now. Buildings don't last forever. The new building's very nice, but that was at the heart of the campus. The new building's peripheral. There's something uncomfortable about it.
Okay. Well, let's get down to the subject matter, because this is your book, Relativity Plus, which I read over the Christmas break, and I have to say it cleared up a lot of sort of gaps in my knowledge with regards to understanding energy and gravity. But we're going to start by talking about space and energy, because you believe the two are so fundamentally interrelated. And if just for those who aren't familiar with particles and atoms, basically everything in the universe is made of matter, which is molecules. If we drill down further, you have atoms, and atoms are made of particles. And particles are the fundamental thing that everything is made of. But you believe that a particle is essentially light. Am I right in thinking that?
In a way, it's better to say energy, but in a nutshell, yes, light. If you, for example, look at the simplest particle, the electron,
Okay, we've got a diagram here.
there's an experiment in physics that's called pair production, where you start off with a photon of light, essentially light.
And light has no mass. It is a wave in space.
It's a wave in space.
Okay. And carry on, John.
Essentially, you split it over an atomic nucleus, and if you get it right, the result is an electron and a positron.
So you fire a piece of light into the nucleus of an atom, and you create matter from light. So we can see in the diagram there that this photon is somehow creating mass, but the photon contains energy. Is that right, John?
Yeah, it conveys energy momentum. That's the better term, but yeah, it conveys energy. And energy is something rather unique. It can be neither created nor destroyed.
Okay.
You can create matter, you can destroy matter, but you cannot create energy. You can't destroy it either.
Okay.
And I think one of the issues is that when you ask, what is energy, the stock answer is the capacity to do work. And that doesn't quite get to the bottom of it. It is something quite unique, and it's intimately related to space itself.
Right.
When you look at a piece of steel, such as a spring, and when you compress the steel, you know that steel is usually an alloy of carbon and iron. The energy hasn't gone into the carbon atoms, it hasn't gone into the iron atoms.
Okay.
It's in the gaps in between.
Right.
It's in the space.
Okay.
Every time you chase down where the energy is, it's in the space.
Right. And in your book here, you define in the barest essence, energy is a volume of stressed space.
That's the end of the line. That's where you get. You look at a region of space that is called, for example, an electromagnetic field, but when you look closely, there's nothing actually there. There are no particles in the space.
And one thing about space itself, people fall into the trap of thinking that if they get some space, a piece of space with no particles in it, they think that that's nothing. it's not nothing, is it? Space is, well, dare I bring in the word an ether? You don't, physicists turn off at that word, don't they, John? But
They do.
It's not nothing. I mean, that's...
This is it.
Yeah.
Space has its vacuum energy.
Mhm.
It isn't the same as nothing.
Mhm.
It was Einstein in 1920 in his Leiden address
Mhm.
who talked about the ether of general relativity.
Right.
Nowadays it's typically called the vacuum
Mhm.
or space itself,
Mhm.
or even sometimes the Higgs substance.
Okay.
But it's not nothing.
Mhm. And one of its properties is that it can propagate and transmit energy in the form of waves.
Yeah, it has an elastic nature. You
Yeah.
can find it in Maxwell's original papers,
Mhm.
where he talks about the elastic nature of space.
Mhm.
A
Okay.
wave runs through it.
Mhm. So we've got space, which has these phenomenal properties that it can transmit energy via, well, we call them photons, but it's essentially a wave in space, an electromagnetic wave. So how does the energy then manifest itself as matter?
In essence, you make it go round and round. You
Okay.
make the wave go round in a circle.
Mhm.
A good experiment that demonstrates this is something called pair production.
Mhm.
Pair
Okay.
production is where you, in essence, throw light at an atomic nucleus, and the result is an electron and a positron.
Okay.
You have to get it right. The energy's got to be right. If you don't put in enough energy, you don't create the two particles. If there's
Okay.
only just enough to create the two particles, they annihilate very quickly.
Right.
If there's enough energy to separate them, then you've created two
Okay.
matter particles out of light.
Now, just for those who aren't informed on this, an electron is a particle which has mass. It has weight. It is stuff, in other words.
It is.
Albeit much smaller than a proton atomic particle, but it still has mass. So you've created...
It has less mass, but actually it's rather bigger than a proton.
Right.
In essence, an electron is light going round in a circle, whereas a proton is something rather tighter.
Okay. It's a higher frequency
Yeah.
as well, isn't it?
Higher energy.
Higher energy. Okay. And so if we were to drill down into the electron then, what would it consist of? A photon in some kind of a knot? Is that what you...
In essence, it is a kind of knot. It's something called the trivial knot in topology. It isn't a simple circle. There are two rotations. It's going round in one direction, and it's going round in another direction.
Okay.
As a result, this photon is trapped. It can't get out.
Okay. And in a wave, or a photon, or any wave, you have a crest and a trough. And I guess it's in a knot in such a way that the crest meets the crest. You know, it's contiguous wave, I guess, if you see what I'm saying.
It isn't like a surface wave on the sea.
Yeah.
There aren't crests and troughs per se.
Right.
The way that electromagnetism is described by Maxwell leads one to think it's, in essence, a twist and turn field. And when you look at the typical electromagnetic wave, it's telling you the degree of twist and turn. In essence, it's telling you the slope. So rather than the photon being a wave, it's actually more like a pressure pulse.
Okay.
You can imagine it as a lemon-like distortion going through space.
Okay.
Now, a distortion you can think of as space warp.
Okay.
If space warp travels through a region of warped space, its path will bend. Now, if you can make the photon travel through itself, it bends and keeps bending and bends forever.
Okay.
The photon is going round and round, only we don't call it a photon anymore. We call it an electron
Okay.
or a positron.
And just to quote one of the explanations in your book, mass is a measure of the amount of energy that is not moving in aggregate with respect to the observer.
Yeah, that's essentially how it is. If you ask a physicist, he'll tell you that mass is a measure of a system's energy content. There's a symmetry between momentum and inertia. The photon doesn't have any mass, but it does convey momentum. Now, if you make that that energy momentum go round and round, the momentum now appears as inertia. You can see this, a demonstration of this in the form of a gyroscope. If you waggle a gyroscope that isn't spinning, it's easy. It waggles easily. If you spin it up, and if you then try to waggle it, it resists motion. All you've done is you've added motion to the gyroscope, you've added energy momentum to the gyroscope, and as a result, it's harder to move. When you have a more complex spin, then that inertia, rather than being called angular momentum or angular mass, it's just inertial mass. If you consider a cannonball in space, if it's moving at 10 meters per second, it's hard for you to stop it because it's got momentum. If, however, it's motionless, but instead you're moving at 10 meters per second, it's hard to get it moving because it has inertia. That demonstrates the symmetry between momentum and inertia. It depends on who you say is moving.
Right. Yeah. Okay. And what evidence do you have that the electron is, you know, as you describe it? I mean, are there physicists that dispute that this is where mass comes from energy tied in a knot?
There are physicists who have written papers describing this, such as Williamson and van der Mark, with their paper, Is the Electron a Photon with Toroidal Topology?
Right.
That was published in 1997. However, it hasn't received much attention and has been rather overlooked. I think it's an excellent paper, and it taught me a great deal. It gave me the insight I needed to be able to explain things in simpler terms for the general public.
Because, of course, this is what they're chasing in the Hadron Collider, isn't it? They're trying to find a particle which is responsible for giving things mass. So you're saying that there isn't, that particle definitely doesn't exist then?
No. The mystery of mass that you read about in the newspapers is really media speak. What you actually find when you read the proper books is that the Higgs field is responsible for only 1% of the proton's mass. All the rest is nothing to do with the Higgs field. And therefore, when you start looking at an electron, the Higgs boson has got nothing to do with it. The photon, which is used to create an electron, is a boson, and that is boson enough.
Right. Okay. All right, then, John. Well, we're going to go for a short break now, but we'll be talking more after this.